Welcome to Microlecture 26, an introduction to stereoisomers and chirality. So stereoisomers are compounds that have the same formula, the same atomic connectivity, but they have a different three-dimensional arrangement of atoms. And so we're going to go through three examples, the last of which is our introduction to chiral molecules. A di-substituted cyclohexane can be considered a stereoisomer if you have, say, one group facing one direction and another group facing another direction. That's not interconvertible with through like a ring flip or conformational change with the compound that has both of those groups on the same face of the molecule, right? So we were calling this situation over here trans, where they're on opposite faces of the ring structure, and this over here, we were calling that cis. And if you have a model built, what you can convince yourself of is that there's no way that you could twist or turn the molecule or shape it differently and allow for this interconversion. Okay, so you would have to actually break a chemical bond. You'd have to break a methyl bond off of the cyclohexane ring and put it back on the other face of the molecule. So for that reason, it qualifies as a stereoisomer, and it's something that you've seen before, so you can relate. Another thing you might be aware of is if you have a double bond, we can also have a trans relationship of groups on that double bond. So if one group is on the opposite side of the double bond as the other group, this is called trans. And if they're both on the same side, then it's called cis. Okay, so once again, we have the same formula, same atomic connectivity, but just a different arrangement. And you'll see if you build the model that you cannot twist or turn the molecule around to get trans to go to cis. You'd have to break a chemical bond. And then the last example that we're going to cover is of chiral molecules. In order to be chiral, the carbon has to be attached to four unique things. So let's have it attached to, say, a hydrogen, a chlorine atom, a fluorine, and a bromine, just to make it clear that there's four totally unique groups. Let's draw the other version of it, where we kind of swap any two of these groups. So I'll draw these two the same, and I'll just swap these two. So now the chlorine is on the wedge and the hydrogen is on the dash. This class of molecules is going to be very, very important to understand. And so upcoming we have a few topics. We're going to be talking about the difference between R and S. So one of these chiral molecules would be called R and the other one would be called S. We'll talk about how we figure that out. And we're going to be talking about what these are with respect to each other, which is non-superimposable mirror images, or enantiomers. And then we'll talk about another class of chiral molecules that have more than one stereo center inside of the same molecule. And so I'll introduce you to the term of diastereomers. So understanding these chiral molecules is very, very important. Here is a real-life example of how chirality has affected our world. This is a tragic example. You may have heard of the drug thalidomide, which was used in early pregnancy for women who suffered from morning sickness in the 1950s. So this is the chemical structure of the drug. You see that one form is called the R enantiomer and the other form is called the S enantiomer of thalidomide. And it turns out one of these forms treated morning sickness very well, but the other form resulted in severe malformations of the baby that was born to the mother who took thalidomide in early pregnancy. So whenever a drug molecule is interacting with proteins in our body, is interacting with any biological molecule, it does so often stereo specifically, and only one of these compounds will actually have the intended effect. So there's a whole area of chemistry devoted to just getting products that are synthesized into the laboratory to get those materials pure enantiomerically. So to have enantiomerically pure pharmaceuticals is a huge area of chemistry, because if there is a stereoisomer or more than one stereoisomer in the molecule that is serving as a drug, we want to make sure that the other form of it, which we have no idea what effects it could have on the body, is not present in that drug.